All right, let's talk about LoRa today. Stands for long range, a little bit underwhelming, but applicable nonetheless. And it's RF, so it's long range wireless communications, typically for IoT. Although we'll talk about some other use cases. Again, it provides or facilitates long range communications using low power. Those two things lead to a low data rate. You can't actually, or it is difficult to have low power, high data rate, and long range. But again, it's just RF, and we typically see this in IoT applications. It operates in the ISM band and is therefore license free, so no regulatory approval required. Here in the US, it operates at 915 megahertz, or the 33 centimeter amateur band. It uses CSS, so chirp spread spectrum modulation, and I'm not going to try to explain that. There's a link to a video that does a far better job than I could in the description below. And I'll reference it again here later. I'll show you a little visualization of it. But it's as opposed to frequency shift keying or amplitude modulation or something like that, it uses chirp spread spectrum. That is difficult to say 3 times in a row. All right, and then another consideration is you're setting up your radio. Or one variable with LoRa RF is the spreading factor. So you can see the chart here on the slide. But effectively, the lower spreading factor, the lower your power consumption, but also lower range. So as you can imagine, it's just a dial, and you're cranking it up from low power, low range to high power, high range. And that's an easy way to think of it, I think. The numbers, I don't know why we couldn't go 0 to 5 or whatever, but here we are. Spreading factor for LoRa radios goes from 7 to 12. So spreading factor 7 to spreading factor 12. And again, this is important for you. This is one of those deliberate variables you want to control for as it affects your data rate, your range, and your battery consumption or power consumption. Okay. LoRa achieves a very high link budget, which means it's the critical measure of range and performance, and compared to other technologies, it is exceptional, with really good receiver sensitivity. So in urban areas, you can get up to 3 miles ish, and that's point to point. And then 15 kilometers, or what's that, 9 point something miles in rural areas. By default, it is just open and unencrypted radio transmissions, and there's some considerations there if you're licensed or not, whatever. That's a different RF class here, but at least at the radio level, there is no built-in encryption by default for point-to-point communications. Now, you can implement that manually, kind of, by making things a little more complicated, and we're going to do some of that today with adding a microcontroller unit or like an Arduino or some controller to be able to encrypt some of the data. And then you can add additional layers of complexity to implement all kinds of features. So like LoRaWAN here, I have as an example at the MAC layer, adds enough complexity to make it a deliberate decision that you should consider or not based on your intended application here, and like weigh the pros and cons of like adding the ability to mesh or encrypt data programmatically, and all the other, and like remote control of devices and stuff like that, if it's worth the added complexity and in your overall system, or if manual implementation of encryption or whatever else you're trying to achieve is actually the better trade-off. Like, is the trade-off worth it? Okay, compared to other common wireless technologies, again, the receiver sensitivity is exceptionally great. Wi-Fi is obviously shorter range and higher speed, but also consumes higher power. You typically have this plugged into the wall, 110 outlet at home. However, like that high speed and the high throughput gives you, Netflix or web browsing or watching this video, for example. Bluetooth is shorter range. I don't know. Actually, should probably adjust this slide. Like, I guess when I think Wi-Fi is maybe medium range and Bluetooth is shorter range. The point is, like, Bluetooth is kind of medium. There's medium speed, lower power. It can last forever. My headphones here last all day long, and I'm able to listen to audio and use my microphone all day without problem. But as soon as I walk, out the door, it disconnects. This is normal stuff that we deal with all day, every day. LoRa, however, I could take my little radio here in my pocket, and I can walk across town and send a message back home, which is crazy, and it lasts for days and days. So this little device has a small battery in it. I'll give you some other examples of implementations or devices that I've got here. But it lasts for, I don't know, off the top of my head, a week. And I can talk to people across town. So it's not a huge town. It's not like a big city or anything, but that's pretty impressive. I'd say I'm pushing the 5 kilometer mark for sure on just this little, battery operated in my pocket device. Really neat. So some real world applications of this might be, or are, metering, and traffic control and other ICS applications. So there's, and I guess that ICS designation kind of covers all these categories. But you'll see this a lot with IoT implementations or sensors. So the sensor itself, like imagine a moisture sensor for a greenhouse or something like that, or a humidity or temperature sensor, some very specific sensor, is really easy to implement, and it can measure the thing, but how do you get that back? And typically that's a bigger system, and LoRa is one of those methods in which you could build out your own system. So you could hook up your humidity sensor to a LoRa radio, given a very small footprint. I've got it kind of spread out here on a breadboard, but you could effectively do this and measure all of your sensors. I can't imagine you just have the humidity sensor in the greenhouse. Like if you're doing this stuff, it's a bunch of sensors likely, and then pump all that back, because you don't expect the humidity to change every millisecond, right? So you don't need a ton of traffic coming across the net, and it's reasonable for you to wait a microsecond to receive that data. It's not like right now critical. It's not like analog breaks where you wouldn't implement LoRa because of the throughput and the transmission rates and all this. You would need analog breaks to be very immediate. However, monitoring humidity in your greenhouse, not so critical time wise. Okay, an example of this, I had AI generate an image here, but I think it kind of depicts exactly that. So you can have one of the big, I guess, hobbyist implementations for LoRa is object tracking or device tracking. So cargo or livestock, your suitcase, whatever. I don't know if they would probably frown upon that. Anyway, So the example I have here is livestock, right? So this farmer from a single pane of glass can monitor where, not only can he monitor where the livestock are congregating, he can monitor usage of the pasture. So where are they congregating? Fine, but what about over time? Like where do I need to move them next? You know, and then with that, you could, well, maybe it's water levels in the pond that they're drinking from, or you name it, right? And he can monitor all that in one place, and that data again gets pumped back to his dashboard, and he can do some predictive analysis on it, and more effectively manage his assets. And then I guess equipment monitoring. So in an industrial capacity, my brother actually uses this stuff for monitoring um, water treatment water treatment valves or sensors at all. So again, like, instead of instead of going into where the water is being treated to figure out what's wrong with the meter, or if the meter is working, or what it's reading or whatever, you have to get that signal out somehow, so that you could just park your van at the site, collect the information, and then off you go. Or you have a repeater or a gateway or something connected to the net, a different net, whether it's the internet or something proprietary, whatever. And again, that keeps my brother and his colleagues from having to go into where the water is being treated to collect the readings, which sounds like a much better way of doing it. Okay, understanding LoRa networks. So I kind of mentioned in my example a minute ago, we have devices like the individual nodes, and those are kind of by default. I guess I should be careful with that word, but like when properly configured by themselves, are create a mesh. They form a mesh. So that's not entirely true. So there's a little bit of nuance to that, but you'll get what I'm saying here, hopefully, in a minute. Then you can add intermediary like devices, and then go all the way up to the application stack where you're implementing something like that farmer's dashboard, and he's doing, he's got it tied into long-term logging and predictive analysis and stuff like that. So the first thing that comes in is a gateway, which is where all the nodes. Imagine it like a collector, and it's a gateway to further things, the network or the application stack. And then you can integrate things with MQTT, for example, and have access to your other IoT devices, and interact with them. Given a parameter, or given a message from your LoRa device, you can interact with something. So like send a LoRa message from my LoRa device to my gateway that turns on the lights on the other side of the house or something. I don't know, plays a beep so that the cows know to come get fed at the barn or something. I don't know. And so when doing that, or I guess when you're working with, I keep showing this. This is a LoRa radio. It's I don't know, the size of my thumbnail with a teeny tiny antenna. And again, this goes 3 miles in my town. So I don't know, that still kind of baffles me. But when you're setting up your radio, whether it's through programmatic, like programming the code with a MCU or something to control it, or you're doing it yourself, there's a couple things you need to consider. One, you need to buy the right frequency for your region. Again, like that's legally speaking, but so 915 megahertz here. So make sure you get the right frequency for your region, so that you can legally and safely operate. And then the spreading factor we talked about, like that tuning knob for low power, low range, low throughput, to the opposite of that, like use all the power, send it as far as you can. And then your network ID, and that's what creates this broadcast bubble. I'll call it more than a mesh. Like there's an additional layer that we have to add to get like true mesh and like repeater capability. But but at least the network ID allows us to communicate as a network, which I guess makes it a perfectly appropriate name for that variable. All right, some of the hardware, I kind of keep holding stuff up here, but specifically, these are just examples. Given what you're trying to do, you'll choose the same or different options. I got some pre-made stuff here. So here's the Liligo T-Beam S3. That's what that looks like. And again, it's battery operated. I find that this one doesn't last nearly as long as I would hope for it to. So that one kind of just stays plugged in around here. And this is my like home node that I can send back to from elsewhere. And then I've got a couple of Muzi work devices, and these are really neat. They've got some 3D printed cases around them. This one here has a display, so I could just, and buttons, which is nice. I can kind of click through. I don't know if you can see that on the video, but there's a little bit of data that I can elicit straight from the device. But both of these are used. They Bluetooth connect to my phone, and I can use an app. These are actually Meshtastic implementations. Again, that's adding an additional layer on top of raw LoRa. But what I get with that is true mesh, repeating. I can plug in my license, I'm a ham operator, KB3PLH. And so I can plug that in and take advantage of like extending the frequency limitations or power or other things. It doesn't matter. But by default, I can just load Meshtastic, use my phone to send messages back and forth across town or in the neighborhood or whatever I'm trying to do. And then this Reyax RYLR998. This is the specific radio that we're going to use in our demo here, and there's a link to a GitHub repo that has all the code for the demo and a link to buy this radio. No affiliation, is just what worked for me in this case. And again, like teeny tiny, size of my thumbnail-ish, and super capable. And I guess one thing, I'm going to back up just a sec, like this is all kind of, it's really exciting and fun because you're playing with RF and it's a super cheap barrier to entry. So you can get everything you need here for, I don't know, don't quote me, look at the links, check it out. And as long as you're willing to put in a little bit of work, you can get like a whole mesh radio network going on or monitor your sensors from across the farm for next to nothing. All right, and then I held this up earlier, but this is our custom setup. So I've got Arduino Nano. It's the ESP32, so it outputs 3.3 volt. So everything on the board runs at 3.3 volt, which is typical for IoT stuff. And the bigger or not ESP Arduino Nanos run at 5 volts. So you have to you have to worry about that and you have to manage it, right? So I went with the Nano ESP so that we didn't have to worry about voltage. Everything's 3.3, everything works at 3.3, and it just makes it a lot easier for our particular setup. Okay, yeah, I've got the Arduino, the LoRa radio, and then a display just for bling, and so we can like do some capture the flag kind of stuff with it, and we can visualize the messages going from client to server without necessarily needing to be connected to a computer, though that's what we'll do in the demo. All right, so those are the devices, and then again, make sure you have the right power supply. Here's another implementation of my device here, and I've got a power supply for the breadboard here with jumpers for 3.3 volts. So again, just making sure that I'm operating at the right voltage for the equipment that I'm using. All right, and then here's a little bit better picture than me holding it up to the camera and trying to explain it. So I've got the Arduino here, the LoRa radio is here, and then the display showing some of the messages coming in and parsed there. Okay, so there's a couple ways we can, so if we start with our Arduino IDE here, we can do a couple we could do a couple demos. I've got my client and server. I guess let me open one more, and I'm going to start by, I'm just going to get straight into the demos. So, go back. There is the AT commands. So the AT commands are how over serial we control the radio. Now, when the Arduino is hooked up, it's sending those commands. So our interaction is just monitoring that serial feedback that we've programmed, for it to print to us. But I can also just interact straight with the radio. So let me see if I can get that hooked up real quick for you. And I'm going to turn on my server, and we'll try to interact with the server. All right, so you can't see it here, but I'm just taking, again, my radio with the USB to TTY connection. I'm going to plug that into my USB hub here. And I'm going to open up the Arduino IDE, and let's do a new, no, yeah, that's fine. Let's do new. And then you can use all kinds of stuff. I find that this one works good. So let's do that. It looks like that's my serial port. And then I can open up my serial monitor here, and I'm good to go. So I'm connected to something. I think that's the only serial device that I have plugged in, so that's got to be it. How I can test. All right, so I've got my radio hooked up. This is my empty sky. I haven't uploaded anything. There's no Arduino to upload to. I'm just interacting with the radio itself. Now, every radio is going to come with a manual, and you should RTFM, read the full manual. That's what that stands for, right? But so this applies to our radio that we bought, and it'll be a little bit different for each manufacturer model of radio, but this one is ours. And here's an example of what I was saying, like the network ID bubble. So as long as you're in the bubble, you can hear the messages broadcast or point to point from each other. If you try to go point to point with a different network ID, it's not going to work. So the network ID is critical, and I don't know if I've said that enough. And it offers us the ability to, it's like being on a different Wi-Fi channel, right? Like, so we're not stomping over each other. So this address 108 and this address 108 can coexist right next to each other if they're on different network IDs. So it gives us a little bit of separation in addressing, and we're not limited to just the amount of addresses that are available. Okay. This is the sequence of using AT commands. First, I guess let me pull up my USB device here, or my raw radio, and what I'm going to do is I'm just going to type AT, enter, and as long as I get an OK back, we're golden. So everything's working as intended. I am connected to the radio, and if I continue reading the manual here, so I can do AT address. And I get an error, right? So this is to set the address. And that was totally on purpose. Again, AT, I get the response, okay, cool, that happened. So what I'm gonna do is set a couple things. Let me get the network ID. So right now, if I go AT plus network ID question mark, and I ask the radio for what its network ID currently is, it's going to tell me it's 73. And I could do the same for any of these commands here. If I just add the question mark instead of the equal sign, then it gives me what that value currently is set to. All right, so I'm going to that's fine. I'll leave it as is. No, I'll show you. So let's change the address. So let's do AT plus, and now this is my radio's address, not my destination address. It's my radio's address, and I'm going to change it to 101, for example. And I get back okay. And I guess it's maybe not obvious that happened. So let me do it again. I clear my serial monitor, do it again. Okay, and I get okay, right? So now my radio is on network ID 73 and its address is 101. Now, before I go on, I'm going to turn on my server here that I have configured based on the code, again, available with the GitHub link down below. And it's going to run through some stuff on the display here. It's going to tell me that it's ready to go. And that's it. Okay, it's already ready to go. So all these commands have already been sent, and the Arduino is sitting there interacting with the radio to transmit and receive as needed. So what you're going to see here, like in a second, is that's going to beacon out a flag. So this is going to be used in a capture the flag type scenario, and so it's beaconing out a message with the flag. Obviously, this is not it. That would be too easy for you, right? All right, so it's going to beacon out, and my radio that I've connected here is receiving that. This is not connected to anything. This is just running on a 9-volt battery by itself. The Arduino is doing all the work, the work of controlling the radio. All right, so that beacon is happening now. There's another element to this. Again, if you look through the code, or you're involved in the in our capture the flag, or you want to talk about it more, reach out. But there's other flags available, and so what I'm going to do is I'm going to try to send a message to my server. Let's see if I could just do this. Okay, I was trying to read and talk at the same time. That never works. Oops, no, that's right. Let's do. All right, so what I have here is I want to send a message. I guess I could pull it up here. Okay, so I'm going to send a message to an address with data, and I have to know the payload length. So with a max of 240 bytes. Okay, so send to address 50, the 5 characters, HELLO. Okay, so we're doing 10 characters, and it's hello there. And my server address is 4. So I'm going to go ahead, I'm going to wait for one more beacon, clear, and then send. So wait for one more, just so that I can have a clean serial monitor here. All right, let's go for it. We'll be able to distinguish. Yeah, there it is. Good. I knew as soon as I made a move. All right, so clear serial monitor. I'm going to send hello there. And immediately, almost immediately, I got the response from the server. So my server, as you can see, again, in the code in the GitHub repo for the server, is set to listen for this exact message and respond with a message of its own. So those could be whatever you want, right? Like, so, and that server could actually be responding to something else. Like, in our humidity example, maybe the message is humidity, and then you send that to the server, and or send it to, I guess, the whatever's monitoring the radio or the server that's configured to monitor the humidity sensor. And when you send it from maybe your home, you send to the greenhouse humidity, it sends you back the value of that sensor, for example. I'm making stuff up on the fly here, but you can imagine, like, there's this interaction that is possible through the programmatic interaction between you've programmed the Arduinos to interact in a way that you intend them to, I guess is what I'm trying to say. And so all of this is built in the code in the repo. I think I've said that enough times. Please check it out. Let me know what you think. But this is, again, I'm able to do this with just this small, tiny radio and a USB adapter. So pretty neat. I'm going to disconnect that, and I'm going to show you what the similar function. So the server's doing the same thing, but I'm going to programmatically do everything else with my client setup here, right? So let me plug this in real quick. And so one of the first things that it does is change the baud rate. So from what is it, 11,500 or yeah, 115,200. That was a dumb way of saying what I just said. It changes it down. It changes it down to 9600 baud. That's easier for me to communicate with the. It's easier and more reliable for the Arduino to communicate with the radio that it's connected to, given our setup. Okay, so I've got my client here. I'm actually not even going to pull up the server part, so let me close that out of the way. And again, so I received, in this configuration, I had a flag that I received just for hooking it up and powering it on, which is nice, and that shows up on the display, and then you can see that in the picture of my slide here. This is what I'm looking at here, and so this 2222 is from the server. So the server is beaconing out to our network ID, and because I've joined the right network ID, I get that beacon and receive the message and parse it based on the code that I've written. Okay, and then there's an additional function built in that with the press of a button sends a message, that crafted message, the hello there message earlier that we did, to the server, and I should receive number 3. So there we are. So there is flag number 3, and again, as you see on the display here, that's exactly what I'm seeing on mine right now, and that was given, effectively this command to the appropriate address on the appropriate network ID, and the server was set to respond given those parameters and that message content or that payload. Okay, and again, that could be anything, so pretty neat, and again, like, you can buy devices that are ready to go. You can interact with it raw for relatively cheap and simple implementations, or you can build out complex systems that monitor your entire farming operation. So lots of range there in what you can do with any of this. I'm going to go back one slide real quick, because this picture that I have here is an actual analog sensor for 4 to 20 milliamp, which is very common in industrial applications. So those meters and gauges and everything that I was telling you my brother monitors, this is an implementation for those kinds of spaces where it's measuring that 4 to 20 milliamp signal and reporting out. So pretty slick. Okay, and then again, like, there's some advanced tuning that you can figure out. There's a exceptional explanation of the chirp spread spectrum. Wow, that's so tough. But the CSS. Watch the video. It's short, it's sweet, it's really good, and there's like a visualization of what CSS looks like down there for LoRa messages specifically. And it's a really good video. It's neat to watch if you're into that kind of thing. All right, and then the spreading factor. Remember that knob that handles like power, data rate, and distance to low to high, and then security. We talked about a little bit of manual encryption. It's in the code that I've written. I did an example of what that would look like. An actual implementation of what that would look like, but then the ability to add like LoRaWAN or Meshtastic or any other like Mac to application layer complexity on top of the raw LoRa RF would offer you some additional features like that. Again, just kind of depends on what you're going to use it for. All right, and then in conclusion, it's a fantastic choice for low range, low power, and versatile RF comms. It's easy to get into building out entire systems using this. I'll give you a head start with I've got all the links for the custom board and everything. All this is linked in the GitHub repo, along with some instructions, not everything yet. And the picture, the wiring diagram, and obviously the code to get started. So you could pretty quickly get something up and running. And then again, read the manual. It's not a ton of information. It's everything you need in 9 pages or less. So that's fairly reasonable as far as technical manuals go. All right. And then, like as a bonus, if you happen to be doing a CTF or competition where this hardware is involved, then you've done the right thing by watching this far. And I encourage you to go check out the GitHub repo. Please, if this video was at all helpful, hit the like button for me. And worst case, just go download the code and start playing around and have fun with it. I hope you learned something.